Welcome. On this video, we're going to be discussing slant asymptotes of rational functions. So let's get started. Let's start by looking at the small introduction question, which states, let's perform the following quotient, and by quotient we mean division, and let's describe the behavior of the remainder as x approaches infinity. So here we have our rational function. And we're doing a division. So we have a polynomial divided by another polynomial. So let's start by performing this division. And for this, I'm going to be performing long division. So let's just set it up. The numerator goes inside the box. The denominator goes outside the box. And let's just perform our multiplication. So x, what do we need to multiply to get x squared? Well, that's x. So it multiplies x times x, so that's x squared. 1 times x, that's positive x. And remember, when in long division, before we combine, we need to change the sign. So that's a minus. That's a minus. If we combine, the x squares are going to cancel out, which is exactly what we wanted. And if we combine, we get negative 2x. And now we ask ourselves, x, what can I multiply to make it into a negative 2x? Well, we're missing a negative 2 here. So if we multiply one more time, x times negative 2, that's negative 2x. 1 times negative 2, that's negative 2. And again, in long division, before we combine, we switch the sign, so this becomes a plus. That becomes a plus. Now let's combine. The two x's are going to cancel out, and what's going to be left is just a 2. So this is what we call our remainder. And since we have a remainder, then we know that x plus 1 is not a factor of x squared minus x. So what we can do now is we can just rewrite our function. Since we do have a remainder, we can just rewrite our function by the result that we got on top of the division, x minus 2, plus the remainder, which the remainder is 2, divided by what we needed to divide by, which is x plus 1. So to get this expression, all we did was I got the result that I got from the long division, x minus 2, and I added the remainder, which in this case it is 2, over what we needed to divide by, which is x plus 1. Let me just get rid of this. Now, all we have shown is that f of x, it is possible for us to write down f of x as this expression. But what we wanted to concentrate here is what I'm going to be calling the remainder term, which in this case, it is 2 divided by x plus 2. So let me call this the remainder term. Which is 2 over x plus 1. And what we want to see is what happens to this remainder term as x goes to positive infinity. So what happens to this whole term as x becomes larger and larger? Well, let's take a look in here. So the 2 is fixed. So the numerator, it's always going to be fixed by 2. Now the denominator is going to start getting larger and larger. And notice as my denominator is getting larger and larger, the whole number is getting smaller and smaller. 1 divided by 10 is definitely larger than 1 divided by 100, which is definitely larger than 1 divided by 1,000. So notice that as we increase our denominator, the value of the fraction decreases. So if x is getting infinitely larger, then it's going to eventually reach the value of 0. So what we have shown here is that if I take a look at the remainder term and I let x goes to infinity, then my remainder term is just going to go towards 0. And we're going to be using this idea when we're going to start looking at slant asymptotes. But let's just put this on the side and we're going to come back in a second. Because now, if you want to have a discussion about slant asymptotes, then the question is, when do we have them? So when do we have slant asymptotes? Well, in a rational function, comma, slant asymptotes, they occur when the degree of the numerator is exactly 1 degree greater than the denominator. Which, if we take a look at the question, or at least the rationale in our introduction question, notice that the degree of the numerator, it is of degree 2. The degree of the denominator, it is degree 1. So therefore, the degree of the numerator is exactly 1 greater than the denominator. So we should expect to have some kind of a slant asymptote. How do we find that slant asymptote? Well, let's take a look at example 1, which notice that example 1 talks about the same example that we did on our introduction. And let's use the result from the introduction. So we have already shown that f of x can be written out as x minus 2 plus 2 over x plus 1. And I'm going to be using this result. Now, to have a better picture about the graph of this rational function, let's start by defining the vertical and the horizontal asymptotes. So for the vertical and for the horizontal, we're going to be using the original rational, which is x squared minus x over x plus 1. So remember that the vertical asymptote happens whenever my denominator is equivalent to 0. So let's just get our denominator, and let's just set it equal to 0. So therefore, minus 1, x equals minus 1. So there we have it. So we know that we're going to have a vertical asymptote at x equals minus 1. Now for the horizontal, remember from the previous lesson that if the degree of the numerator it is greater than the degree of the denominator, then there is no horizontal asymptote. And again, this is because the degree of the numerator is greater than the degree of the denominator. Now let's talk about the slant asymptote. And for the slant asymptote, we're actually going to be using the result that we got from the division. So let me just rewrite it down here. And for the slant asymptote, I want for you to think about the following. So what happens to the function f of x as x goes to infinity? So we're saying, if I take a look at this function, is there a line or is there a point that is approaching as x is getting larger and larger? Well, I know one thing for sure. I know that as x is getting larger and larger, the remainder term gets closer to 0. Because that's exactly what we have shown here. Notice that we said if I take a look at my remainder term, as x becomes larger and larger, this whole term goes to 0, therefore we can just say that it disappears. So my conclusion then is that if this term, if the remainder term, as x is getting larger and larger, it just gets closer and closer to 0, then we can kind of say that as the limit of f of x, as x gets infinitely larger, well, it just gets closer to the line x minus 2, which is what we had on our result from the long division. So anytime we suspect that we have a slant asymptote, and again, slant asymptotes, they only occur when the numerator is exactly 1 degree larger than the denominator. The remainder term, it's always going to disappear, or it's always going to go close to 0. And what is left here, that's always going to be the line of your slant asymptote. And let's show to see if that is true. So let's actually sketch this. So let's go to our decimal activity, and now let's graph the function x squared minus x over x plus 1. So here we have the graph of f of x. Now, we're saying that we have a vertical asymptote at x equals -1, so let's just put that in there. Yeah, that seems to be the case. We seem to be having a vertical asymptote at x equals -1. Now, we're saying that we have a slant asymptote. I guess I didn't define it here. I'm sorry. I guess I'm just going to put it here. The slant asymptote is the line y equals x minus 2. So if this is my function, well, let me graph the line y equals x minus 2. And notice that this also seems to be an asymptote, but the difference is that this asymptote is neither vertically or horizontally, it is diagonally, and that's what we call a slant asymptote. And it seems to be the case that x minus 2 is the line that my function f of x is getting closer and closer to it. Just notice, I'm just dragging it, and it just seems to be getting closer and closer. It does fit the description from the right, and if I move it from the left, it also fits the description on the left. So this is how we can define slant asymptotes. We can just perform some kind of division and then take a look at the results. Let's do one more example. So let's try to graph this function f of x. And again, the first thing that I want to see is, can I simplify the function? Well, it doesn't seem the case, because I can definitely factor out the numerator as x plus 1 and x minus 2, but that's not going to cancel out with the denominator. So I cannot simplify this any further. Okay, now that we have that out of the way, I take a look. Well, my numerator, it's exactly 1 degree greater than my denominator. So therefore, I should expect to have some kind of a slant asymptote. So let's find all the asymptotes, which are vertical, horizontal, and slant. So for the vertical, again, we just set our denominator equal to 0. So x minus 1 equal to 0. Let's add 1 to it. Cancels out. So I should expect to have a vertical asymptote exactly at x equals 1. For the horizontal, notice that we already stated that the numerator, it's the degree of the numerator, it's larger than the degree of the denominator. Well, I want to say the degree of the numerator, it is larger than the degree of the denominator. Since that this is the case, then we have no horizontal asymptote. Now, to define the slant asymptote, we're just going to perform our long division. So let's just do that. So we got x squared minus x minus 2. And we're going to put x minus 1 on the outside. And let's perform our long division. So x, what do I have to multiply to make it x squared? Well, in this case, it's going to be x. Let's multiply that. X times x, so that's x squared. Negative 1 times x, so that's negative x. And before we combine, we got to switch the sign. So let's switch the sign. This is a negative. That's a positive. They cancel out. They cancel out. And the only thing that is left is negative 2. So let's just bring that down. So this is my remainder. So what we have shown is that now this function f of x, I can rewrite it as what I got from my division, which is x, minus 2 over whatever we were dividing by. So we know that f of x can be written this way. And now this is my remainder term. So I know that my remainder term is going to go to 0 as my x is getting larger and larger. So therefore, this is the line that is going to be approaching. And this is the line that we're going to be defining as our slant asymptote. So therefore, the slant asymptote is just the line y equals x, which is exactly what we got here. So let's sketch our function and let's see if our slant asymptote and our vertical asymptote is correct. So let's go to decimals now. So here we have the function that we started graphing, or they started discussing, x squared minus x minus 2 divided by x minus 1. So this is the actual graph of this function. And now we're stating that we have a vertical asymptote at the line x equals 1. So let's just graph that. So here we have it. Yes, it seems to be accurate. We seem to be having a vertical asymptote at x equals positive 1. Notice that if we zoom out, yep, it fits the description of a vertical asymptote. Now let's graph the function y equals x. Well, notice that that seems to be an asymptote as well, because if I just look at the behavior and if I move my graph to the right hand side, notice that it's just getting closer and closer to this line, y equals x. It's not going to cross it, it's just getting closer and closer. So it fits the definition of an asymptote. And the same goes from the left hand side. Notice purple dotted line is my asymptote, y equals x. And if I just keep scrolling to the left hand side, my graph, which is shown in green, is just getting closer and closer to this asymptote here. So yes, we can define a slant asymptote as y equals x. So with this, we conclude our lesson for slant asymptotes of rational functions.